This is the Mechanics Homework Booklet, question 34. Part A. State in words how the force acting on a body is related to the change in momentum. Quite simply, this is a form of Newton's second law, and you should state that force equals rate of change of momentum. Part B. A football of mass 0.42 kilograms is moving horizontally at 10 meters per second towards a footballer's boot, which then kicks it. The figure shows how the force between the boot and the ball vary with time whilst they are in contact. First, you are asked for the significance of the area under the line. Quite simply, looking at the axes of this graph, force and time, you should appreciate that the area under the graph relates to multiplying force by time, and that must represent the impulse. The impulse is also equal to the change in momentum of the football, so either answer would be correct at this point. Next, you are asked to estimate the impulse that acts on the ball, and you are asked to state an appropriate unit. So what you need to do to find the impulse is estimate the area under the graph. This can be done in a variety of ways. You could approximate the area under the curve to the area of a triangle. And you can see how in drawing the triangle I've tried to compensate for where the triangle is an overestimate of the area bound by the curve and where it is an underestimate. So approximately these two areas are equal and these two areas are equal. So then it's just a matter of calculating the area of a triangle using the equation a half base times height. So we have a half multiplied by the base, which is 250 milliseconds. Notice you need to look at the axes to realise that you need the power times 10 to the minus 3. The height of the triangle that I have drawn corresponds to 85 newtons. That gives us a final answer of 10.625. Alternatively, you could estimate the area by counting squares underneath the curve. I've just begun a rough estimate by putting a number in the squares that are complete or nearly complete. That leaves me to 20 squares, and then looking at the remaining spaces shown, I feel that 22 would be a good representation of the total area. So I have 22 squares, and the value of area corresponding to each square is given by its height, which is 20 newtons, multiplied by the base, which is 25 milliseconds. This leads to an answer of 11. You were asked to estimate this area, and the mark scheme would allow anything of 11 plus or minus 1. Don't forget to state the units as you were prompted, which would be Newton seconds. The next part of the question asks you to calculate the speed of the ball after it has been kicked. We are told to assume that it returns along the same horizontal line it followed when approaching the boot. And we are asked to consider an appropriate number of significant figures in our answer. Here you are applying the physics principle that the impulse equals the change in momentum. If you are uncertain how to begin, looking back at the previous part of the question would prompt you to realise you have just worked out impulse, and you should think, how would this be relevant? Now we want to find the speed of the ball after it had been kicked, so that is the final velocity. And the impulse equals the change in momentum, which equals the final momentum, take away the initial momentum. The difficulty here is in correctly applying the sign convention. So I have decided to take everything towards the foot as positive. I'm thinking of that as to the right in my mind. So the initial velocity of the football was 10 meters per second towards the foot, so that is plus 10. The final velocity I don't know, and the impulse was 11, but I know this is the impulse due to the force of the footballer's kick, which will be in the opposite direction to the initial velocity. Hence I've given this a negative sign. Also relevant here is the mass of the football at 0.42 kilograms. So having written a general statement first, I now carefully substitute my data. So I have a negative impulse, or I can think of that as to the left, must equal the final momentum, take away the initial momentum, which is positive since it was to the right. Rearranging that and bringing this over to the left-hand side changes a minus sign to a plus sign, and that leads me to an answer of minus 6.8 corresponding to the final momentum. Dividing this by the mass of the ball gives me again a negative answer and a value of 16.2 for the final velocity of the ball. The negative sign here corresponds to the fact that this velocity is in the same direction as the force and in the opposite direction to the initial velocity. I've rounded this to a value of 16 so that I am matching my significant figures with the values I had in my data. Don't worry about which direction you consider to be positive. You can't make a wrong choice here. It's just important that you're consistent, that you apply the same convention to every piece of data. So had you taken to the left as positive in this case, that would have switched the minus 11 to a positive value. The final momentum is still the unknown, and then the positive value that we took away here would become a negative value, and two minuses together would lead to a plus in this position here. Note it leads to exactly the same numerical answer. Finally, you are asked to discuss the consequences if the ball had approached the boot at a higher speed, but still received the same impulse. Following through the logic, we can say that the final speed would be lower. The reason for this is that the initial momentum of the ball would be higher, and since the change of momentum is the same, and the initial and final momenta are in opposite directions, this leads to a lower value at the end. You may need to spend a little bit of time convincing yourself of these marking points. So consider the ball approaching the foot and then being kicked back in the opposite direction. If it approaches with more initial momentum, that momentum must first be removed, bringing the ball to a halt before it can then change direction and increase its momentum to the left. So if it started with more momentum to the right and there's only a certain total change possible, there will be less left to accelerate it towards the left.